So yes, so let me introduce you to the rest of the class. Yeah, Shashank Arago is a very well-known researcher in the field in cryptography. I think in Joe Bonneau's class, we quickly talk a little bit about you, about the fact that you're also a friend of Harmony, mostly through Aaron, another instructor behind the course. So yeah, why don't we just start? I let you share your screen, I think.
Give me 1 second.
Yeah.
The sun is shining like directly into my eyes, so I have to wear a cap.
I see. Yeah. I also have to turn the blinds on. Some of the students are from all over the world, so they might be a bit jealous of our sunshine situation in California. It might
I
be
see.
at
Right.
night or something.
When I try to screen share, it says that host has disabled it.
Oh, yeah. So we make Shashank host as well.
Okay, so I'm host now.
So we'll talk about something related to proof of space-time and Chia and Filecoin today. That nicely follows from the VDF class a couple of weeks
ago. Yeah, it seems that I will have to restart Zoom.
Oh, okay.
Yeah, it seems because I have never shared screen with Zoom before. So I just gave it permission and I'll have to restart. Yeah, I'm sorry. Just give me a moment and I'll join the class.
Yeah, no problem. Yeah, let's do that. So good to see everyone here. I think that means that we are in the phase of doing a final project. But these few classes, I think just 2 classes remain. They would cover some of the infrastructure building issues that might be interesting to those people who want to join the course next time or help teaching. So, all right, shall we make you a host again, Shashank?
I think I am able to share. Let's see.
Yeah, good.
Do you see my screen?
Yeah, that's right. Good.
Okay, cool.
Thank you.
So yeah, I don't think I've met anyone in this class before. I'm Shashank. I work for Western Digital, and previously I've worked for Visa Research. I do a lot of crypto-related stuff, and I also work on cryptocurrencies. This is something storage-based cryptocurrencies is something that I started working on last year when Chia came out actually, and Western Digital got really interested in what Chia does and how it works, because the sales of their hard drives and solid state drives, it went through the roof. So they got really interested all of a sudden. And that's how I got involved into this. And it's a very interesting area to look at. So I guess in this class you have, by the way, am I audible? My voice is clear, right?
Yep, we can hear you all right.
Okay, cool. Yeah. And please feel free to stop me at any point and ask questions. I don't mind being interrupted in the middle of the talk. That's the only way I can know that somebody's actually listening. Right. So I was saying that in this class, you might already have seen, basics of blockchain and like the importance of zero knowledge proofs. But, proofs in cryptography, they serve all kinds of purposes, right? It's not just about showing that you know something or hiding what you know. It's also about showing that you have something. So like proof of work could be thought of as you having access to a certain amount of computational resources. And a proof of storage that we'll see today, it's about proving that you have access to a certain amount of capacity, storage capacity. And there is nothing to like hide here. So there is no zero knowledge aspect here. It's just about showing that you actually have dedicated a certain amount of capacity to a certain blockchain network, right? Okay, so let's start. Wait, why does it not? Okay, yeah, agenda. So I'll start with some basics of blockchain. And I think I'm going to go through this very quickly because you guys might already be familiar with all these things. And I'm going to focus on what sort of different cryptocurrencies, storage-based cryptocurrencies are out there. And why is it difficult to build a storage-based cryptocurrency? I think this is a very important thing to realize. And if you can get an idea of why this problem is so difficult, I think that would you should consider yourself to have learned something about this class. Then we'll talk about two specific cryptocurrencies, Chia and Filecoin, and then some others if we have time. And finally, I'll make a short remark at the end. Okay, basics of blockchain. I'm going to go through this quickly. Like I said before, you probably already know all about this. At least the Bitcoin blockchain is a chain of blocks. Sorry. Yeah, and if you zoom into a block, you would see that it has a bunch of transactions. Yeah, I was also supposed to, head of the chain and stuff. Right. And blockchain actually takes many different forms. So Bitcoin blockchain is certainly a chain of blocks, but not every blockchain is like that. You have blockchains that have different kinds of structures. That there could be a graph-like structure or something else. And a blockchain is not just for sending some tokens to each other. You can do a lot more on a blockchain. And you have all these different blockchains that support smart contracts, arbitrary smart contracts. Then you also have blockchains that are tied to some real world asset, like stable coins, USDC, Tether, Terra, and so forth. And although it's generally believed that blockchains are like very wasteful, very slow, some blockchains can be quite fast because of the consensus method they use and some of the design choices that they have made. But there are some core properties that we have come to expect from a blockchain. And one of the important properties is decentralization, right? There is no central authority, no single point of failure. The network is open for everybody to participate, right? Anybody can join or leave at any point they want. Auditability is another important aspect, right? Anybody can go through the transactions in a blockchain, all the blocks, and they can verify that everything makes sense, everything is valid, right? You can, a lot of these blockchain companies, they have made their code open source, so you can even go through the code base to ensure that it has the desired behavior, that there are no backdoors and stuff, right? And of course, for the operation of the network, you don't have to trust a node or a collection of nodes, right? In particular, this is important, right? There are no secrets that need to be protected in a blockchain network, and there's also no expectation that most of the nodes will follow the rules. They can. Some of the nodes can deviate, and we would still have a functioning network. But the problem is, if you have this open setting where no one trusts each other, how do you actually agree on something, right? And it's very important to agree on something if you want to make progress. For example, you may have all these unconfirmed transactions floating on the network, and different nodes in the network would have different views of the activities on the network, right? So said they would each see different sets of unconfirmed transactions, and if you want to make progress, you would have to pick some transactions, confirm them, right, and then move on to the next set of transactions. But if different nodes in the network have different views, and also you don't really trust each other, how do you reconcile these differences? How do you come to an agreement? And it's not an easy problem. You might think, oh, let's just talk to each other as we do in the real world. But the problem is it doesn't quite work in an open setting. There might be too many people to talk to, or you may not even know who you should talk to. It could be really slow. So what a lot of blockchains do, instead, they they choose someone as the leader in every round and let them propose a block. And if the block satisfies some basic conditions, some basic validity conditions, then you accept the block and move forward, right? And then the question is, of course, how do you pick a leader? One option that at least these top blockchains like Bitcoin and Ethereum have is to use proof of work. And you know, we all know how proof of work works. But there's a massive amount of energy consumed in the process of generating these proofs of work. And people have said that the amount of energy consumed by Bitcoin is comparable to entire countries, right? So are there good alternatives to this? And this is where storage-based cryptocurrencies come in. They could help you find, or they could help you get an alternative to proof of work, but they can also be used for a lot of other things too. There are at least two different types of things that you could do with the storage-based cryptocurrencies. One on the right-hand side is, of course, consensus. You can base leader election on the amount of storage capacity that someone has dedicated to the network. And more capacity would translate to higher chances of you being elected as the leader. So this could act as a good alternative to proof of work. Hopefully, right? We'll see how it works, but it could be a good alternative to proof of work, right? Hopefully it will help us save some energy. The other option, the other way people could use these storage-based cryptocurrencies is to actually get decentralized storage. So you could use the blockchain to connect seekers, by which I mean people who are looking to store their data, and providers who have some extra capacity to store their data. So you have seekers, you have providers, people looking to store data, and people who can store data, and the blockchain could help them connect with each other. And the blockchain might also store the contracts that they set up with each other. And this is also something that seems useful to have. It puts spare capacity that these providers have to good use, right? So in a cryptocurrency, you could have both of these things or just one of the two things. Filecoin is an example of a cryptocurrency that is both a decentralized storage system, so it connects seekers and providers with each other, and it also uses storage as a means to reach consensus. Chia is an example where storage is only used for consensus. It's not a decentralized storage system. And there are cryptocurrencies that are only decentralized storage. Chia Coin, RB, Storage, they use some other method for consensus. So the first question that you need to ask here is that are these cryptocurrencies that are based on storage non-trivial to build? Like, given that we understand how Bitcoin, Ethereum, etc., they can be built, how difficult it is to build something that is connected to storage. Okay, let me stop here for a bit and see if anybody has any questions. Any questions at this point?
Hi, I have a question.
Yeah, sure.
So what is the difference between decentralized storage, which uses the blockchain, and IPFS? Both of them offer decentralized storage, but IPFS does that without a blockchain, right?
Right. With the blockchain, you can do a lot of things on top of this, right? You can provide the right kind of economic incentives. You can also use the blockchain to like store everything, track everything. We'll see. So you can, for instance, you can use the blockchain to track proofs of space, proofs of space, time, or storage, and make sure that the person who's storing your data still has your data.
Okay, thanks.
Does that make sense? Yeah. And
Yeah.
for all of that, the seeker, the client who has stored the data, doesn't have to be online. Even others can others can check these proofs of storage on the behalf of the seeker.
Oh, okay. Yeah, that makes
Yeah.
sense.
Yeah, we'll see
Thank
some
you.
of that. Yeah. So yeah, cool. Okay, so let's get into the difficulty of building a storage-based cryptocurrency. And like I said, there is at least two aspects to this, right? You could have a storage-based cryptocurrency that acts as a decentralized storage system, or something that can also be used for consensus. Okay, so first of all, what does a good decentralized storage system look like, right? It should be able to connect seekers with providers in an open marketplace, right? Everybody can join as a seeker or join as a provider, and they should be able to connect with each other. All the contracts should be recorded on the blockchain, and they should be automatically enforced. And then you would also expect data storage and retrieval to be reasonably fast, also reasonably cheap. And a very important point here is that seekers should have enough confidence that providers haven't lost their data. This is very important. So there should be some continuity of storage. If seeker stores its data with a provider, then as time passes, the seeker would like to know or be sure that the provider still has their data, they haven't lost, right? That's important. So if you have these properties, you might be able to get a good decentralized storage system. Okay, so let's focus on the last point here. How would seekers how would a seeker be get confidence that provider still has its data? So they could do something off the chain, for instance. They could like talk to each other every now and then. The seeker could say, look, could you reveal some random portion of the data for me, right? Like seeker, if seeker has stored a file with some n blocks, like 100 blocks, with the provider, seeker could say, oh, could you show me that you still have the 13th block or the 20th block or something? And the provider would just send the block back to the seeker. And I'm sure you guys know about Merkle trees and stuff. So the seeker might just hold on to like a Merkle root of its data, and the provider could provide a path in the Merkle tree to show that this 13th or the 20th block is indeed part of the file. But the main problem with this approach is that seekers have to be online, right? They need to be online to talk to the providers to make sure that the proofs are correct and stuff, right? And there are other problems with this approach too, but I'll just mention this one problem. Now, instead of doing things off the chain, you could also move on the chain and do the same type of thing, right? The benefit of moving on the chain could be that the seeker may not have to be online. Maybe other people on the chain who are part of the network can verify the proofs that a provider provides. But the problem is that, are you really going to store all these proofs, all these Merkle paths on the chain? It could be too much, right? And it could make the blockchain slow. Okay, so what about the second aspect of this? Can we use storage-based cryptocurrencies to build like a storage-based consensus system? Okay, so what does a good storage-based consensus system look like? First of all, anyone should be able to contribute storage capacity to the network, right? And the more capacity you contribute, the higher chance you should have of being elected as the leader. And the important point here is that no one should be able to fake capacity, because the capacity that you dedicate is going to be used for consensus. So you should not be able to show that you have dedicated a gigabyte when you actually have only dedicated a byte, right? That's very important, because we are going to use storage for consensus. And anyone should be able to verify how much capacity you have dedicated to that. Right? This is what a good consensus system based on storage should look like. But it's not easy to build this either. Like if you think about it, how would someone show that they have allocated or contributed or dedicated a certain capacity, say cap, to a blockchain network, say X? The very first problem you would face is that how to show that this capacity cap is being used only for the blockchain X and not for any other network, right? And like maybe what you could do is to fill up this capacity with some data, right? And you show every now and then that you still have the data. So for instance, you might fill up your capacity of 1 gigabyte with some data. Like, where does that data come from? We don't know. And you prove on the blockchain that you still have the data. But like I said before, this is going to make the blockchain slow, right? If your proofs are not small enough, it's going to make the blockchain bloated. Okay, so yeah, who provides the data? And how to make sure that it cannot be compressed? If the data is coming from somewhere else, like if someone else provides you 1 gigabyte of data to store in your spare capacity, what if you are able to compress it? What if you are able to compress that 1 gigabyte of data to a byte and just store 1 byte, right? That won't be ideal. And if you say that the data comes from someone else, like who is that person? In a blockchain world, someone else could just be you, right? You could do like a self-dealing kind of thing. You could just send your data to yourself and show that, look, I have 1 GB of data, but really all you need is a very small capacity to store it. So you might be able to fake that you have actually stored 1 GB of data. So you have all these problems, like convincing somebody that you actually have dedicated a certain capacity and nothing less is not an easy task. Okay, any questions at this point? Does it make sense what I'm saying so far? Hello?
Yeah,
I
it makes
think,
sense.
I think on the text,
Okay.
some people type something, but yeah, general, I think it's very clear. Actually, I find it very, very useful so far.
Okay, yeah, cool. Yeah, just wanted to make sure that everyone's with me. Yeah, all right. So let's look at 2 particular cryptocurrencies, Chia and Filecoin, and see how they handle these problems. Chia is a fairly new cryptocurrency. It was launched last year in March. And out of all the cryptocurrencies that I know, this has the highest dedicated capacity, about 35 XB bytes. The market value of all Chia tokens is also quite reasonable, very large, like $2 billion. They use some interesting terminology that you wouldn't find in other blockchains. They don't use the word mining. They use the word farming, and instead of saying scripts or contracts, they use the word puzzles. In Chia, the main thing that people do is to generate plots. So you have miners, or in this case, you would call them farmers. They generate plots on a constant basis. And they don't even have to, it has not much to do with how the blockchain is growing. The blockchain is growing on its own, and you just keep generating plots. The more you generate, the better it is for you, because it's going to help you in consensus. Each plot is about 100 gigabytes, and it's filled with some sort of semi-random data. So the plots, they don't store any real data. You fill up your plots on your own. And the data stored in those plots is only meaningful for consensus in Chia. And like I was saying before, farmers generate plots on their own, starting from some seed value. I'll talk a bit more about this in a bit. And plotting involves hash computation So at a high level, plots cannot be compressed. And it used to take several hours to generate plots when Chia came out, but it's much faster nowadays. So Chia is an example of storage-based consensus. You're using storage for consensus, but it's not a decentralized storage system. In Chia, it's not possible for me to like store some meaningful, useful data on the Chia network. That's just not how it's designed. It's really people generate plots and use plots for consensus. Right. So what happens at every round in Chia? In every round, a challenge becomes available, and then the farmers, they start looking through their plots to see if there is any plot that they can use to respond to the challenge. And the response is what you would call a proof of space. And it's very short. It's only 256 bytes. And of course, it's much, much smaller compared to the plot size of 100 gigabytes. And 100 gigabytes is actually their smallest plot. You can create plots that are even bigger. And there is some notion of a quality of a proof of space, and out of all the proofs of space that are proposed by different farmers, the one with the best quality is going to be added to the chain and would earn some rewards. There's also another interesting thing here, which is that some sort of artificial delay is introduced into the block generation process through the use of PDFs. It prevents some attacks on the Chia network with the use of PDFs, and it also provides some time for the network to like synchronize, right? If you notice, like with proof of work, it actually takes time to compute proof of work. But with proof of space, this plotting thing happens in some sense offline. And when you want to use your plots, you need to, you generate this proof of space, which is actually really fast. If you have a plot, then you can immediately like get a proof of space out of it, at least for Chia. So, you need to somehow slow down this process. And VDFs help you to slow it down. So you have this alternating sequence on the Chia network where a proof of space is generated, then you have a VDF computation, then another proof of space is generated, then a VDF computation, and so forth. And the better quality proofs that you have, the less number of VDF iterations that you would do.
It looks like we have a question in the chat.
How is
quality? No worries. How is quality measured?
Right. To measure the quality, they say that I think you sort of hash the proof, and it has to, the smaller the number you get out of the hash, the better the quality. So similar to how you have in proof of work, right? Your hash is supposed to start with some number of zeros. So it's kind of similar to that.
Okay, thanks.
Sorry, so essentially it's a kind of random, arbitrarily defined, but I mean, it's not, there is an orderly defined, so someone would have deterministically have a better proof, but it doesn't reflect anything that is intrinsically valuable. Is it right? So
yeah,
quality.
it's just, yeah, quality is not some, you're right. Quality is not something intrinsic. When you see a bunch of different proofs on the network, you just need to have some way of comparing them, right? And quality is kind of computing a random function of that. You apply hash to all these different proofs, and the smallest number that comes out, it also determines how many VDF iterations you're going to do, and the smallest number that comes out, that proof is considered to be of the best quality.
So it's a bit like in proof of work networks. There's a bit of randomness as to who is lucky enough to have generate the highest quality. And does it correlate your plot size? If your plot is very big, then you have a higher chance of getting a high quality proof, or is it unrelated?
Right. No, they are related. So first of all, one farmer doesn't have to generate like one plot. You can generate as many plots as you like. And the most basic plot is of 100 GB, I said, like I said before, but you can generate plots of larger size, or you can just generate 100 different plots of the same size, 100 GB, right? That's up to you. But the more plots you have, the higher chances you will have of being able to find a proof in your plot, given the challenge. Right? So it could be the case that if you have one plot, you may not even be able to find the challenge in your plot. You need to first find a challenge. And the more plots you have, the higher chances you have that you will be able to find the challenge in the plot. And if you find like 5 different or 10 different proofs of space from all the plots that you have, you just pick the one with the best quality, send that to the network. And of course, other people would also do the same. And then, the best one would be picked up.
So let's see. So I think Sam, I want to follow up with it. Would I be able to do better than the random users by using more CPU and permutating my plots to get a better hash? Yeah. So instead of I think the idea here is that you try to force people to have more storage, right? So it's equivalent to, or not, to incentivize them to have more storage, just like in Bitcoin, you incentivize them to have more machines. But I think Samra has a question. If you're very clever with a smaller storage, can you somehow use a better CPU and GPU to somehow?
So that's a very good question, and your question would be answered in just a bit. So once you look at the construction would give you some sense of why it's kind of hard to do that. This plotting process is designed in a way so that if you don't store the entire plot, it would be really difficult for you to respond to any challenge. Yeah, they want to make sure that you have to store the whole thing, not even like half of it or like 3/4 of it. You have to store the whole thing if you want to have any reasonable chance of responding to a challenge. So let's look at the construction for a bit. It might seem a bit weird, but hopefully you'll get something out of it.
Thank you.
So how does plotting work? Every plot is associated with a secret key called a plot secret key. And there's something called a plot ID that you define with the help of the plot public key and a few other things that I'm not going to get into. You hash all of that and you get a plot ID. And now the entire plot is somehow generated deterministically from the plot ID. So you're kind of expanding this plot ID, which is just 256-bit hash, right, to 100 GB. Wait. Okay. Right. So when you're generating these plots, the goal is that it should not be possible to produce proofs unless someone has stored the entire plots, right? After all, it's about proving space, right? So the first idea, which doesn't quite work, is something like this. It's also about computing a hash function, but think about doing it offline, right? Not when the block is available, like in Bitcoin, right? You're doing this offline. So pick some random behaving function, say f, that maps a domain of size n to a domain of size n, and somehow it incorporates the plot ID. We'll see that later. And you could say that a plot is defined by generating the entire function table of f and say sorting it by the output. So that suppose that defines your plot. You generate the whole function table and sort it by the outputs. And given a random challenge, say y, you have to find an x such that f of x equals to y. Right? Now, if the entire plot is available to you, you can look at, because it's sorted by the outputs, right? You can quickly find y in the table by doing a binary search. And once you have found the y, you can find the corresponding x and respond to it. Okay. So and this is, if this is your plot, right? You might wonder, like, can I store a fraction of the plot and still be able to like respond to some challenges, right? You might wonder. And in fact, there are people have looked at this problem before, and it is indeed possible to trade off space for time. In particular, suppose if you have like S bits of auxiliary information available, and you have you can make T calls to this function f, then it is possible to invert the function in roughly n cubed time, which satisfies this relation. So it is possible to have SNT, which is like, for example, n to the 3/4, and you would be able to invert the function. So you don't actually need to store the whole thing. If I give you a smaller amount of storage and I give you some time, then you would still be able to invert it. Does this make some sense, right? So this was already known, and it has been known for like, I don't know, 20, 30 years, right? So here's a second idea. This was proposed in a paper in 2017. It looks slightly complicated, but it's actually not that complicated. Suppose you define two functions. Now, instead of one, you have two functions, f and g. The first function is defined as a hash of the ID. ID is the plot ID that I was referring to before, and some x, and you restrict it to L bits. Then you have another function that takes two inputs, x and x prime. By the way, can you see my mouse pointer? Yeah, okay. A hash of ID and x prime, again restricted to L bits, and given a challenge y, the prover is supposed to provide three things: an ID, x and x prime, such that x and x prime are different. F is same on both x and x prime, and the value of g on x and x prime is equal to the challenge. Suppose this is how we define a set of two functions, f and g, and this is how you're supposed to respond to a challenge. Then let's say how you would generate a plot to respond to the challenges quickly. You would first generate a table that has entries x, fx, sorted by the second one, right? And then you can use this table to find all x prime such that fx equal to fx prime, right? So if you have generated a table with x, fx, and sorted by the second entry, it would be easier for you to do the second step, right? Find all xx prime such that fx is equal to fx prime. Now, for all those x and x prime, you compute g of x prime, right? And store these three triples, again, sorted by the third value. And the expected size of this table would be roughly 2 to the L. Now, given a challenge, you know what you have to do, right? You just look at the third column, which is already sorted. With binary search, you would be able to quickly find out if you have the challenge y in your third column, right? And then you just look at the corresponding row, and you will see x and x prime there, and you already know that f evaluates to the same value on both x and x prime, right? So you would be able to respond to the challenge. So that's good. And in this case, with this particular construction, which is more complicated than the one that we saw before, you could actually prove better lower bounds for this time and memory trade-off. You can prove better lower bounds, which is shown in 2017. So Chia actually goes a step further. They make this construction more recursive, you could say. They use a nested version of this construction to even further minimize time-space trade-offs. So instead of like, I mean, you could think of the first construction as like one table. This is like two tables, and in Chia, actually, they have 7 tables. And you are supposed to look for challenges in table number 7, and then you sort of find x and x prime in table number 6, and for each of those you find something in table number 5, then table number 4, and go all the way up to table number 1. So you have 7 tables, and the proof consists of 64 values. That's what a proof looks like. So the construction is a bit complex, and the hope is that for this particular kind of construction, you wouldn't be able to trade off space for time so much. You would effectively have to store the entire thing.
Yeah, excuse me, Shashank. I think a student
Yes.
has a question and asked whether we can go through the one table example, maybe again more slowly. I also
You mean
just
for this one or for the previous one?
I think the previous one. Sema, can you think about the last slide, right? Or what is the one table example?
Could you go through the one table example again? Oh,
Yeah.
the one table example. You mean this one? Oh, sorry, this one. The one table example, if this is what you're referring to, then one table example is just you compute the entire function table of X. So you compute F for every input value, and then you store it by sorting it based on the output. Does that answer your question?
Yeah, so it's basically just a function. Basically, and the ideal property of the function is that basically it's random and people cannot predict it in advance what kind of
yeah.
fraud.
So somehow, if you again comparing it with Bitcoin is very helpful. In Bitcoin, when you have a new block, you also have to compute hashes, but the hash computation there depends on what's inside the block, right? You take the hash of the block and use it in your, you have to find a nonce and you have to use the hash of the block in that process. But here, the blockchain thing is separate. You're computing hashes starting from this plot ID, right? There's nothing else that you have to take into account, just the plot ID. And plot ID is something that you can pick yourself. It's not something that comes from outside. You pick whatever plot ID you want. First you pick a plot secret key, from that a plot public key, and hash it to get a plot ID, and then just start plotting. Right? And these hash functions here that are used to define the functions, F and G, these hash functions, they also take plot ID into account.
I have a question. So
Yes.
the hash functions are designed to be collision resistant, right? So how will you find x and x prime such that fx is equal to fx prime?
Oh, because you don't take the whole length of, like, you restrict the length of the hash output. So hash function here might produce 256 bits, but L here would be smaller, say like 32 or 33 or something. In fact, for Chia, for this 100 gigabyte plots that that I've been mentioning, L is 32.
Okay. But
Yeah. So
if someone has a lot of storage and if someone uses less storage, so shouldn't L be different for both of them?
L is something that that is sort of determined by the Chia protocol. L has to be at least 32. You can pick 33, 34. The higher L you pick, the bigger your plot becomes, and it grows exponentially. So like for 34, 35, 36, suddenly it becomes like terabyte and stuff.
Okay, yeah.
Yeah, it has to be at least 32. That was a good question. Yeah. So yes, H is collision resistant. It is supposed to be a random behaving function, right? But at the same time, you restrict the length of the output to just 32, and that's why you're able to find collisions. Okay. All right. So hope this gave you an idea of what Chia plots look like and how do you do proof of space for these plots, right? And it's important to keep in mind that you just generate plots for the purpose of consensus. It's not like in any way useful data or anything. Okay, so to conclude this section of the presentation, I want to say that when Chia came out, there was a lot of excitement, and like I said, Western Digital also noticed that their sale numbers were going through the roof. And the price of Chia was also quite high at that time. I think it went above 1,500, and it was there for some time. And the net space also grew at a phenomenal pace. So if you look at the chart here, it was launched in March last year, And in the very beginning, the net space, the amount of space dedicated to the network, which is basically the size of all the plots, right? It grew at a phenomenal pace. And now, of course, Chia is much cheaper. The net space growth has plateaued. It's not really growing anymore, and it has been stagnant for a few months, and it's even like might be going down a little bit. But on the other hand, plotting is much faster. It used to take several hours, and now you can do it in like 10-15 minutes or something, as far as I know. And there are a lot of new features that the Chia folks have been working on, and some of them have been released. All right, next up is Filecoin. Filecoin, I would say, was one of the first serious attempts at building a storage-based cryptocurrency. It was launched in October 2020, but they had an ICO back in 2017, where they raised $250 million US dollars. It was one of the biggest ICOs at the time. The current network, the current storage capacity dedicated to the network is about 15 exabytes, one of the largest, certainly lower than Chia, which is 35, but 15 is still quite high. And the market cap of all these Phil tokens is actually more than Chia. The interesting thing with Filecoin, and this is what makes Filecoin very different from Chia, is that it's both a decentralized storage system, and they also use storage for consensus. So their design is very different. So it's a decentralized storage network where anybody could contribute storage capacity to the network, and anyone could store their data. Right? So you can actually say that, look, I have like this movie to store on the Filecoin network, and you would be able to do that. It has two different markets. There's a storage market where you pay the storage miners to store your data, and there's also a retrieval market. In both these cases, clients, they place bid orders, and miners, they play ask orders, and the Filecoin market would help match the orders in a decentralized and verifiable way. So like I said, if you compare this to Chia, it's very different. In Chia, everybody sort of fills up their disk with their own data, right? And by design, all the data that's stored is just like junk, right? It's only useful for Chia consensus. But in Filecoin, at least in theory, people can store their data on the Filecoin network, and the storage capacity that's being used for storing all this data could be used for consensus. Right. The basic unit of storage on Filecoin is a sector, and they support two types of sectors, a 32 GB and a 64 GB sector, and mostly I see 32 GB. And the maximum lifetime of a sector is 18 months, but you can extend it. Now, here is where the interesting stuff starts. You actually have two types of sectors. There's a regular sector that contains client data, and there's also a sector called a committed capacity sector that contains no data. So it can contain, for example, all zeros. And Filecoin actually encourages miners to take advantage of all the available storage that they have immediately, even before they can find enough clients to use this space. This is an important point to note, actually. So if you have some spare capacity, don't wait for a client to provide you data. Make your capacity or turn your capacity into committed capacity sectors. A sector that is filled with just zeros, for instance, but you're somehow able to dedicate that to the network. But you know, there are a lot of problems here. Like, how does the network know if a miner is actually dedicating 32 gigabytes of space towards storing a sector worth of data? Right? How does the network know? If the data is coming from someone else, right? It might be possible to compress it. Like a client might think that my data, like I have a movie, right? Maybe my movie can only be stored. It would take up the entire sector, but the provider might be smart and might be able to compress the data, might be able to store that same movie in like 10 gigabytes or something. And what if the client says, look, you have to store multiple copies of my data for redundancy reasons. In that case, the miner could actually get away by just storing one copy, right? And the problem gets worse for committed capacity sectors, because those sectors are not even supposed to store any real data. They can just be zeros, right? So how do you, from a network perspective, how does the network know that someone who claims to have stored a sector actually dedicates 32 GB to storing that sector? So ideally, if a miner claims to contribute X sectors to the network, they should actually dedicate 32x GB of disk space towards it, right? So do you understand the problem, right? Filecoin's approach here is an interesting approach. They actually expect miners to seal the data in such a way that it takes a long time to seal. And it actually requires 32 GB to store the sealed data. So the raw data might actually need a very small amount of space to be stored. But once you seal data, and sealing takes a long time, it would actually take 32 GB to store the sealed data. And then they ask miners to periodically and quickly prove that they still have access to the sealed data. And all these proofs, they are made really, really small using fancy cryptography. Of course, not fancy for you guys, but using fancy cryptography like snarks, these proofs are made really, really small. I don't have slides here to give you some idea of how sealing and these things work, but let me try to just say that in words. The high level idea is at least kind of simple. So starting from, you're given a file to store, and the file might be just, think of it as all zeros. So what you don't need any space to store all zeros, right? You just know it's all zeros. But sealing works like this. You start with the file, maybe compute a hash of the file, and include a few other things in the hash to get a fresh seed value. And you have to generate a bunch of randomness from the seed value. So if you have, for example, say n blocks in your file, then you generate like n blocks of randomness starting from the seed value. And your seed data could be defined as the original data XORed with the random blocks. So if your original data is like all zeros, you can just ignore it, right? So your seed data is basically all these random blocks. But there's already a problem here, because if this is how you define sealing to be, people don't really have to store anything, because when you ask them to show that, can you show me like the 20th sealed block, you would quickly compute the 20th random block by just computing this hash thing. Hash, maybe your hash function with the seed value was taking 20 as an index. So in that case, it's very easy to just compute the 20th random block, XOR it with the original block, which is just zeros, and then you have the seed block. So you wouldn't even have to store any data. So the way you derive randomness from the seed value has to be more complicated. One option could be like chain the randomness. You could define a random, like 20th random block to depend on the 19th random block, which depends on the 18th random block, and so forth. This also doesn't work because people could still get away by just storing like alternate blocks. You could store maybe 17th block and 19th block and 21st block and so forth. From that, if you have the 19th block, you would be easily able to derive the 20th block. Right? You don't have to store it. So you have to make sealing even more complicated. So what they end up doing, they use something called depth robust graphs, where to derive a random block, you don't just use the corresponding raw block. You make the random block depend on a number of plain text blocks, and you sort of keep doing this over several layers. So they have this sort of randomized graphs over several layers to finally derive the random blocks. And then once you have the random blocks, you XOR it with the original data to get the seed data. So this by design is supposed to take a long time, so that if you get rid of your seed data, if you delete any portion of the seed data, it would take you a long time to regenerate it. And in that time, you would basically miss the opportunity to provide these proofs of space. Yeah. Sorry, I spoke for too long. If you have any questions, feel free to ask. I don't have.
I suppose go a little bit beyond, but go ahead. Questions.
Yeah, I did not have slides. I thought I already have too many slides, so I did not include slides on the technical details of how this Filecoin sealing works. But this is the sort of the high level idea.
I actually find your explanation very useful. And maybe because I'm not a computer scientist myself, the conceptual part actually was very clear to me. Was even maybe better than going through the more complicated details. Someone wanted to ask a question earlier. Yeah,
does this mean that?
Go ahead, Kuzik.
Yeah, please.
So does this mean that only half the data on the network is useful data? The other half is random data?
Why do you ask? Oh, no. Oh, so the miners are supposed to only store the sealed data. They're not supposed to store the raw data. Given the sealed data, you can sort of go through the same process and unseal it.
Okay, got it.
So there is no source of randomness here. The seed for deriving the random blocks is actually derived from the raw data itself. But to make sure that the seed is fresh for every copy of the data or for different copies of different data is to include other things in the computation of the seed. So you not only include a hash of the raw data, you also include like miner ID and sector ID and those things. Yeah. So like if you have a client who says, store 5 copies of my data, you don't want the same seed to be derived in every case. So you would assign like a different number to each copy so that your seed comes out to be different. And if your seed is different for each copy, then all the random blocks you generate from the seed will also be different. So for every copy, you would actually have to.
Data,
Yeah,
so when you're retrieving the data, you compute the seed again and then use generate the random data again and then reconstruct the original data.
Yep. Yeah, that's how it is. That's one way to do it. Yeah, you can of course choose to store both your there's also that's how you would do it. Like they don't focus. So okay, here's my from what I have understood, they don't focus so much on retrieving data. If you go through Filecoin documentation and other stuff, you will see that they don't focus so much on retrieving data. Their focus is more on how your data is stored and how proofs are made about the data stored. But how the data is actually retrieved, it's not something that you would find much information about. But yeah, one option would be that recover the sealed data and then unseal it the same way you sealed it. All right.
Okay, thanks.
So yeah, sure. Moving forward, now thinking from a miner's perspective, a miner might have dedicated or might have created many different sectors, right? Hundreds and thousands of sectors for different clients or different seekers. So how does all of this is taken into account? Well, you have every 24-hour period is broken down into a series of 30-minute deadlines. So you have 48 deadlines in any given 24-hour period, and every miner is supposed to show the availability of all the claimed sectors on a 24-hour basis. Every miner for all the sectors. the sectors a miner has, they are assigned to deadlines and they are grouped into partitions. So if you have, say, 1 million sectors, a miner has somehow created 1 million sectors, then all these different sectors, they are, every sector would be assigned to some deadline, and all the sectors that are assigned to a deadline, they are grouped into partitions. So you have, in a partition, you have like 2, 3, 4, 9 sectors. And when there is a deadline, a miner is supposed to prove something about a whole partition. So what you would see on the chain is like a snark proof for an entire partition, one snark proof for one partition. And these snark proofs, what are they showing? So they are basically like under the hood, it still proves based on these Merkle trees. So the challenges are still like, oh, for this sector, show me the 20th block, show me that you still have the 20th block or 25th block or so forth, and give me the Merkle path to the root. So that's what it's kind of like under the hood. But of course, you cannot put all these Merkle paths for like all these sectors on the chain. So you use the snark technique to compress all of this into something very short, and that's what goes on the chain. So from a proof perspective, it takes a lot of work to generate these proofs. But yeah, from a verifier perspective, and also from a blockchain perspective, right, it's very efficient. Right, and like I said before, if you delete any portion of your sealed sector, the sealing is done in such a way that it would take you too long to regenerate the sealed sector, and by that time you would miss a deadline. Right. So a sector goes through different stages during its life cycle. It starts out as being pre-committed, where the miner seals the sector and submits this message miner.precommit sector on the blockchain. Then it proves that it actually has done the sealing properly. That's when the sector becomes committed. Then the sector moves onto an active stage where proofs are generated for the sector time to time. The sector could become faulty, recovering, or it could also terminate. Okay, now the consensus part. So far, it was mostly about the decentralized storage part. Now the consensus part. So note that all the sectors from the previous slide, you might have got this, like all sectors are recorded on the chain. So you would be able to see on the network who has contributed how much capacity. So now the leader election is going to be based on how much storage capacity you have dedicated to the network. The more power, storage power. Yeah, so the more storage capacity you have dedicated, the higher chances you will have in any round of being elected as the leader. So here they use a source of randomness because they call DRAND, and they use some VRF type stuff here for someone to show that they were the ones who were chosen leader in this round. And whoever is chosen as the leader, they get to mine a block, they earn a block reward of 25 FIL. Right. So now I want to make some comments on Filecoin. And the mission of Filecoin was to create a decentralized, efficient, and robust foundation for humanities information. But you could ask, like, how much useful information is actually stored on Filecoin, right? So if you recall, I spoke about two different kinds of sectors. There was like regular sectors where you store real client data, and there's also committed capacity sector. So you could commit any amount of capacity to the network, but how much of it is actually someone's data. So we can quickly look at the chart here. Let's see if, yeah. Yeah, this chart here. So on this chart, you can see that, can you, yeah, I hope you can see this. Yeah. So on this chart here, you can see that there's a lot of proof commit sector, pre-commit sector, and a lot of proofs happening. But when you go down to this publish storage deals, there's a very small fraction of storage deals on the network. So this kind of gives you an idea that the number of deals that are happening on the network between clients and the providers is a much smaller fraction of the number of committed sectors that are being committed or dedicated to the network. So most of the capacity that is being dedicated is actually empty. It's nobody's data, and there's only a very small number of actual storage deals on the network. Okay, right. So why does this happen? It happens for a few different reasons. First is that people don't want to pay a lot of money for storing their data, and the storage fee is actually much smaller when you compare it to block rewards. Of course, these days the price of all these cryptocurrencies has gone down quite a bit, but at least a few months ago, block reward is 25 Filecoins, and that is worth a lot more than what you might get from storage fee. So people are motivated to just commit capacity so that they can increase their chances of being elected as the leader and earn these block rewards, right? They don't want to wait for somebody to provide them data. And also storing the data of someone else comes with some operational overhead, which the miners may not like, right? So you are in a situation that's not ideal, right? It was meant to store like real data, but what's actually on the network, you have all these sectors that just store nothing, or in other words, it's all sealed data. And what is sealed data? Just hash outputs, right? And sealing is also very expensive. A sealed sector is what, 32 gigabytes, but to actually seal a sector, you need 128 gigabyte of memory and 480 gigabyte of disk space. And it's because of the design of the the process of sealing, where you derive blocks, random blocks, layer by layer by layer. There are like 11 layers, and each layer is like 32 GB. So that's why you need so much space for sealing. And then snarks are used to compress proofs, which also makes proof generation very, very expensive. And the downside of the sealing and unsealing business is that, first of all, unsealing is the same as sealing, right? Filecoin doesn't have good latency. If you want to, if you have stored your sealed data with somebody and you want to like quickly retrieve the data, it's not possible. It's just, if you retrieve sealed data, you would have to unseal it. And because sealing takes too long, unsealing would also take too long. And by the time you have the data, like a few hours would have passed. Right? So it's not a network that is ideal for storing data that you might need at any time. Yeah, unless you store like both, somehow manage to store like a copy of the raw data and sealed data, right? From just sealed data, it takes time to go back to like the original raw data. Okay, I don't know how much time I have left. I probably need like another 10 minutes. Is that okay if I keep going?
Yeah, let's do that. Yeah.
Okay, so I can talk a little bit about some of the cryptocurrencies, definitely not in this detail. So there are cryptocurrencies like Chia coin is one. It's among the top storage tokens. It has a big market cap and a decent amount of storage capacity committed to it. Here you have file contracts that are signed between providers and clients that specify how long is the contract, how often the challenges would be sent out, and how the payment would be made. And it seems that the way proof of space or proof of storage happens here is kind of this basic idea. You ask the provider to like reveal a segment of the file and a list of hashes in the file's Merkle tree. It wasn't clear to me if this happens on the chain or off the chain. If they do it on the chain, then it's going to be not very efficient. There's another storage token called Storage, which is also very well known and has somewhat similar ideas, that that it's built upon. They manage most of the things with the help of smart contracts. And the way they do proofs is, again, sort of the same idea using Merkle trees. RV, I think, is more interesting. They claim to provide permanent storage, and I don't know how realistic that is. And as far as I understand from reading their white paper, is that the data is actually stored on the blockchain itself, which seems to be a bit much, right? If you store something on the blockchain, the actual data is on the blockchain, then it has to be synced across the network, and it might just take too long. And they have also this concept of recall blocks, where whenever you mine a new block, you're not just supposed to know the previous block, you're also supposed to know some random block from the past, which they call a recall block. So you sort of need a hash of both of these blocks, the recall block and the previous block, and maybe more than that, to compute the new block. And the reason they do this is because they think that this would force the miners to hang on to as many blocks in the past as possible, because to mine a new block, you might need any of the one of the blocks in the past. So people would hopefully hang on to as many blocks as they can, which would make sure that your data sits with a lot of different miners in the network. There's also a bunch of other, you could say, marketplaces that are set up on top of other cryptocurrencies that connect clients and providers. Yeah, some of them don't have very good documentation, so there's not much I can say about them. Okay, so I'm on my last slide now. My personal opinion of all of this, I don't want to criticize anyone. I'm not saying that Chia is bad or Filecoin is bad. It's just a hard problem. Like building a good decentralized storage system is hard. And Filecoin was designed very carefully. It has a lot of solid math behind it, but the economics that they don't seem to work. And also, like when Chia came out, it was seen as a good alternative to proof of work. But at the same time, you could look at it and wonder, like you have so much capacity that's being used for Chia consensus, 35 exabyte, and all that capacity is actually not storing anything useful. It's just storing like hash values that are only useful for Chia consensus. So is it any better than proof of work? It's not obvious. So I would say that both these problems, decentralized storage and storage-based consensus, are important problems to solve. And I don't think that they have been solved fully. There is a lot of scope here, and you might certainly be able to improve things. Thank you.
Thank you so much. Anyone got a quick question here? Actually, yeah, I was kind of curious about the motivation in the first place about projects like Chia when they have these basically trying to replace a lot of computation with a lot of space. But in terms of like environmental concerns or energy consumption, because basically getting a lot of space also requires you to pay the money to get the hardware, which presumably also requires the same amount of energy or some amount of energy to produce them, right? Is it?
Yeah.
So is there some, maybe not proof, but some arguments that this is actually better in some longer term?
Yeah, I mean, they have done some analysis. If you go to their website, you will certainly find some information about this, and they do still believe that this is, when it comes to energy efficiency, this thing, their proof of space is more energy efficient than proof of work. Yeah, but like maybe it is somewhat more efficient, but I feel like it can be a lot more efficient. So first of all, you are reserving, you can say, all this capacity for Chia consensus, a whole lot of capacity, like 35 exabytes is something. And also, it's not like it comes for free. Generating these plots also is very resource intensive. Initially, when this came out, it was taking, I think, 3-4 hours to generate a plot, and quite a bit of memory and stuff. So it wasn't easy to generate plots. That part was also resource intensive, but sure, it is one time, and then you generate the plots and keep them around for as long as you want. So if you take all of this into account, maybe it's still a bit more efficient than proof of work. And like I said, you can go to their website and check the numbers out. But there might be scope for making it even better.
And I wonder, is there some sort of attempt at combining the design of both Chia and Filecoin? So you can actually use a Chia-like design and just basically fill up a lot of space with junk, with random stuff, and then from that get the consensus. But can you also use those plots to actually store data later on? So then you would switch, maybe someone would then give up the plots if the demand for data comes in, and you use that to actually fill up actual data. Then would it be a nice solution? Then you don't have the Filecoin problem that people just compete for these registered space and they don't actually get used.
Right. So yeah, people have thought about this, including us. If it's possible to combine Chia and Filecoin, I have not been able to find a way to do that.
I think it's not so trivial.
And to make it work, yeah. But it is something definitely worth thinking about. Yeah. And you still have to make sure that the economics work. As long as block rewards are high compared to storage fees, people would not be motivated to store the data of someone else. They would be motivated more to earn the block rewards. Right? Yeah. Block rewards are tied to how much capacity you have dedicated. So you will have to also make the economic incentives better to make sure that people actually are motivated to storing the data of someone else. There's also more, you could say, the responsibility that comes with it. What if you accidentally lose the data, right? It's kind of hard to, there's also this, when you set up a deal on the Filecoin network, you have to deposit some collateral. And if you miss a proof, every 30 minutes you have to produce a proof. If you miss a proof, some part of your collateral is slashed. So all those things are there, but like it's very hard to place a monetary value on some data. And it may not even be the same for every piece of data. It may be different for different things. And no one wants to lose their data. If you store someone's data and you just somehow lose it, sure, there is this collateral thing, but they might get really upset.
Yeah. I can see why Aviv go to the extreme of just putting the data on chain, but that seems to be quite an extreme solution, as you pointed out. Is there some sort of intermediate solution, like a sharding, like a design, where the data is actually stored multiple copies, but not like as many copies as nodes? So there are like different shards. So then you have some compromise between security and efficiency there.
Right. Again, a good question. I have not seen such a design for any storage-based cryptocurrency. But again, it's something that you can certainly look into. Yeah.
Maybe I should let Samar ask the last question. It's quite interesting. It's about, are there advantages to proof of space over proof of stake? So in a sense, proof of stake was kind of solve all the energy efficiency questions. I suppose it has something to do with fairness, and proof of space might ultimately be more secure and fair. Does it sound right?
So proof of stake seems to be, seems to like not suffer from any of these problems. You don't need any computation, you don't need any storage. But at the same time, if you look at the literature, people have pointed out that it could be attacked in many different ways. Like I know that Ethereum has been trying to come out with some sort of proof of stake system, and it's been taking them a lot of time. I don't know why is that. Maybe it's because they're trying to make sure that there's no way to attack it, right? Like for proof of stake, you can. It's easy to maybe rent stake. You can like borrow a lot of stake for a very short time, and if you have a lot of stake at any given point in time, then you might be able to like create new blocks very, very quickly. There's nothing stopping you. Like there is no, you could say there is no computation or nothing that you have to do to slow you down. That's why Chia has introduced VDFs, right? Just to like slow people down. If it's just proof of stake and you happen to have a lot of stake at any point, you can keep creating blocks and blocks and blocks, right? And you might even go back in time to a point where you did have a lot of stake. You may not have it anymore, and just start. You might be able to fork the chain from there, and you might be able to create hundreds and thousands of blocks in an instant. So there are all these different problems with proof of stake. And I'm not saying that there's no way to solve them. There might be, but you have to like be very careful. If you come out with the proof of stake system, you might have to use other crypto parameters in the right way to make sure there is no attack on it. Yeah.
So hopefully, all of these different methods are all here to stay. And in the end, the different chains will all have different properties, and they all get to work together.
So I'm sorry. Yeah. If there is time, I would like to like point out one more thing, which is also like could be a way to answer your question. So building something like decentralized storage system has its own value, right? It has nothing to do with consensus or anything, because you have people in the world who want to store their data, and you have people in the world who certainly have a lot of extra capacity. I'm sure that you have extra capacity on your own, like laptop or computer. So it's a good idea to connect them. Like that is an interesting problem to solve by itself, right? Forget about all the blockchain stuff or whatever. Right? It's nice to build a decentralized storage system. And if you are able to build such a thing, like why not use this capacity to also reach consensus, right? Like if you design this system carefully, right, you might be able to build the second thing from the first thing in a nice way. You build a decentralized storage system and then somehow use the storage capacity that different people have dedicated to this system for consensus. So that might that sort of also kind of answers the question, right? What is the benefit of proof of storage? So this is not really a benefit, but the thing is, it could be built in addition to something that's useful. Yeah.
I really appreciate your point of view. Okay, thank you so much, Shashank. I hope we will get to see you again in the future. But thank you so much for this class. It's really enjoyable and a lot to learn. Thank you so much.
Sure. Yeah. Thank you. Yeah, happy to be here.
Thank you.
Yeah. If anyone wants to talk about anything else, feel free to email me. I'm happy to talk about these new things. They're new for me too. Like I've been looking at them only since last year. Yeah.
All right. Thank you. And thank you, everyone. Thank you.